Section 16.4, Green's theorem in the plane. You should know definitions of circulation, curl, flux, and divergence. You should be able to apply and verify both forms of Green's theorem, apply Green's theorem to problems, a variety of situations such as area. I'm having a little bit of fun with color schemes in this section. Hopefully you can tell that. More seriously, I'm just going to say here that Green's theorem, this is like a really powerful statement that just kind of is the pinnacle of calculus, multivariable calculus in the plane. So everything here that we're doing in the plane, then the final handful of sections in the book will be, everything will be in space, but this is the big wrap up for the plane. Before we can state Green's theorem, we need to talk about circulation, curl, flux, and divergence. So let's see here. Circulation and flux, those are terms that we saw back in section 16.2. So here is flux. Remember this definition with this is how we calculate flux. And then we have the definition of flow here, and at the end I kind of said if your loop is closed, it's circulation. So the ones that we really care about right now are curl and divergence. And so I'm just going to start off talking about the K component of curl. And in fact, it won't be until later sections that we will get into a full discussion of the curl. So the motivation for the K component of curl is, suppose that you have some kind of fluid flow going on here, and I'm just kind of drawing some vector field F here. Now imagine that we had some little paddle wheel with some kind of little paddle wheel with oars on it, something, and there's a little, we're going to stick it down, like there's an arm, a handle coming out of it, and we're going to take this little paddle wheel and we're going to plop it down in the water here. And the thing that we should realize is that the water is, roughly speaking, rotating in a counterclockwise direction. And so the thing is that we should realize that if we take our little paddle wheel and drop it into the water like this, our paddle will rotate counterclockwise. CCW is counterclockwise. And so this turns out to be exactly the motivation behind the K component of the curl. So here's our definition. The book starts off by calling the circulation density of a vector field F is mi hat plus nj hat is the scalar expression, partial derivative to n with respect to x minus partial derivative to m with respect to y. We also call this the K component of the curl. We'll do, as I said, the general version of the curl later on in the last handful of sections here. So this is the definition. I just give you a vector field F of two variables. It's very easy to calculate out partial derivative n with respect to x minus partial derivative m with respect to y here. But then what does it have to do here? The physical interpretation is, will your paddle rotate at all? And so if the curl of F dot K, if this is positive, if you drop a paddle wheel in, it will rotate counterclockwise. If curl of f dot k is negative, your wheel will rotate clockwise. And if curl of f dot k is equal to 0, the wheel won't rotate. So this is our physical, interpretation. This is what you should be thinking about. You have some kind of fluid flow like water, you stick in a paddle wheel, will rotate. The K component of the curl will tell you whether or not it will rotate. Let's work out some examples here. So remember this picture that I drew back in section 16.2. F of xy is negative y, comma x plus y. It looks something like, we have counterclockwise rotation. Can we see that from our K component of the curl calculations? Well, let's check that. So f is negative y, comma x plus y. The curl of f dot k is equal to the partial derivative of the second slot with respect to x, that's 1, minus the partial derivative of the first slot with respect to y. Subtract minus 1, we get 2. And yes, that's positive. And I just asserted here that corresponds to our paddle wheel will rotate counterclockwise. And yeah, we can see that from the picture here. If you drop in the paddle wheel at any given point here, you're going to have a little bit of counterclockwise rotation going on. Useful if you're trying to operate, some kind of, mill here, trying to get some kind of power going. A couple more examples here. Calculate curl f dot k for f is equal to xi hat plus yj hat. So curl of f dot k is going to be the partial derivative of n with respect to x, that's 0, minus partial derivative of n with respect to y, that's also 0. We get 0, there's no rotation. And so we just think about, what does this vector field look like? Xi hat plus yj hat. Well, let's see here, xi hat, it's going to look something like this. Everything is just moving away from the origin. And so if you drop in a paddle wheel right here, there's equal pressure trying to turn it clockwise and counterclockwise. It's not, your paddle wheel isn't going to turn, but there's no way to get this to turn. There's no way to get this to turn no matter where you drop in your paddle wheel here. So no rotation. And secondly here, f is equal to negative y I hat plus xj hat. Well, that's very similar to what we just did. Curl of f dot k would be the x partial derivative of this is 1 minus the y partial derivative of this is negative 1. Okay, we get 2 again. Yes, there is going to be, counterclockwise rotation. Picture looks somewhat similar to this. Okay, so that's an introduction to the K component of the curl. Future sections will get an overall interpretation of what the curl is, but this will be what we need for Green's theorem in the plane. This is one of our definitions. Next video will have our next definition in it.